after working with linear systems and the three different ways of solving them, the key thing now is to do real life applications. So lesson 6.4, what we're mostly going to be looking at is all the story problems and which type of solution or how we should solve it, which method we should use. We'll be looking at all three of them, graphing, substitution, and elimination, but most of the time, substitution and elimination, as we look at our essentials, understanding. It says, can you solve linear systems using a graph, substitution, and elimination? The best method to use depends on the form of the given equation and how precise the solution should be. Graphing, we can use that for a visual display when you want to estimate a solution. Substitution is when one equation is already given for a variable and it's easy to solve. Elimination is when the coefficients of one variable are the same or opposites, or when it's not convenient to use graphing or substitution. So a lot of times elimination works well for many different systems. One of the things we'll be looking at is what's called the break-even point. So if we look at an equation of your income, and in this case the expenses, we are looking for when do we make money, what's the break-even point. So it says a system of equations is useful in modeling problems involving mixtures, rates, and break-even points. Break-even point, what does that mean? In business, it's the point when income equals expenses. The graph shows the break-even point for one business. It says, notice that the values of the Y, the red line, represent the dollars spent in expenses. The values Y and the blue line represent the received income. So Y is used to represent both expenses and equations. So let's look at a situation. And in this situation, it says a fashion designer makes and sells hats. The material for each hat costs $5.50, and the hat sells for $12.50 each. The designer spends $1,400 on advertising. How many hats must they sell to break even? Well, we want to write a system. X is the number of hats sold. Y is our dollars. It could be expense or income. So for our expense, we are looking at Y equals 5.5x plus the $1,400 that we spent on advertising. Our income is going to be 12.5 or 1250x. So in this case, if we are going to solve these, since they're both Y equals, we could graph, but again, that's not very precise. So the best way to solve this one is when we are looking and substituting the two Y's equal to each other. So Y equals Y. 5.5x equals plus 1,400 equals 12.5. We're going to subtract 5.5x from both sides. 7x equals 140, and x in this case would be equal to 200. So since x is 200, that's the number of hats we have to sell to break even. What dollar amount would that be? Well, in order to find that amount, we would simply replace Y, our income, is equal to 12.5 times 200 to get our other break-even point as we look at that for how much money we would make. So now it's your turn. Here's a puzzle expert. They write a Sudoku puzzle. His initial costs that we are looking at are $8.64. Binding and packaging costs 80 cents a book. The price for each book is $2. How many copies must be sold to break even? So we want to think about our expenses. Our expenses is in this case, the initial cost. And the other thing that we should have is the binding and packaging. So think about how we're going to write that. And it's the binding and package for each book. Our income is going to be the price that we are charging per book. So you should be able to write two equations, put them right below here, and then you're going to solve that system. Remember, we are looking for how many copies need to be sold. We don't need the dollar amount. So look back at that last example if you need to. Another thing that we're going to talk about is identifying the constraints and if it's called a viable solution. So a local zoo is filling 2 water tanks with an elephant exhibit. One tank contains 50 gallons of water and it's filled at a constant rate of 10 gallons per hour. The second one contains 29 gallons of water and is filled at a rate of 3 gallons an hour. When will the two tanks have the same amount of water? We're going to let X be the number of hours it takes to fill the tank and Y is the number of gallons. So our two equations, Y equals 10X, 10 gallons per hour, plus the initial of 50. The second one, 3 gallons per hour, plus the initial of 29. Again, since Y's are equal, we want to set them equal to each other. Now, we go through solving this just like we do our other systems, subtracting our x's, getting them on one side, solving for x, and it says x is negative 3. And I want you to think about that. When will the two tanks have the same amount of water? X equals negative 3. Okay, is that making sense to you? Well, you continue because you're just plugging along and you substitute in negative 3, 10 times negative 3 plus 50, and we get y is 20. So we think the solution is negative 320. Now remember, what was our x? Our x was the number of hours it takes to fill the tank. So the question is this solution, the constraint is, considering when we're writing it, in this case, x has to be greater or equal to 0. Remember, we can't have negative hours. We can't go hours before. So once you've solved, the question is it viable? Such as, is it negative or not? And so in this case, negative 320 is not a viable solution because it is not possible to have time being negative 3 hours. So the tank never has the same amount of water. So it says, when will the tank have the same amount? It will never have the same amount of water. They're never going to intersect. They're always going to be, in this case, what's considered not a viable solution. The last type of problem that we want to look at is the last time that is called the current or wind problems. Now, with these, you're going to talk about both airplanes and boats. When we do that, as we look at the problems for the airplanes, when we talk about airplanes, we talk about a plane travels from west to east in the United States. The steady west to east winds acts as a tailwind. That means it increases the speed. So when you travel from west to east, it's always going to be your plane speed plus the wind is equal to the ground speed. That means the wind's pushing you a little. But when you travel from east to west, the wind, you have a headwind, it's called. This decreases the plane speed. So when you are traveling from the east to the west, it's the speed of the airplane minus the wind speed is equal to your ground speed. That's usually why going from east to west takes you longer by plane than if you're going from west to east. Same thing happens with boats. If you're working with the current or against the current. When you go with the current, it actually speeds the boat up. So when you're going against it, it decreases. When you're going downstream, this increases the boat speed. So read over these notes a few times, pause the video, look it over, and see if this makes sense. When you're with the current, it's the boat speed plus the current equals ground speed. When you're going against the current, it's pushing you or slowing you down. It's the boat speed minus the current. So now we are going to look at one of the wind problems. A traveler lives in Charlotte, North Carolina to Los Angeles, and they're going to fly to Los Angeles, California. At the same time, another traveler flies from Los Angeles to Charlotte. The airspeed of each plane is the same. The ground speeds are shown below. What is the speed, the airspeed, and what is the wind speed? So A plus W equals 550. They were traveling at 550 miles an hour. But on the plane that left Charlotte, airspeed from going from the west, or from the east to the west, A minus W is 495. So what we want to do in both these equations, these are perfect equations for substitution. And we could substitute. The other thing you could do is, for me, I think it actually makes even more sense to simply add the two together. So as we are looking at ours, we're going to substitute in A plus W equals 550. We add these and we find A, where our airspeed is 522.5. Once we have that solution, We're going to substitute that into the first equation, A plus W, and subtract and find that our wind speed is 27.5. So here you can see elimination is perfect for these equations when you have both your airplanes and your boats. Using that elimination method is super easy. It is now your turn. Here, you're going to row about 2 miles per hour upstream. You travel the same distance downstream with a speed of 5 miles an hour. So again, think about, you're looking at the boat. If you look at those equations, you want to think of boat speed plus current equals ground speed. Boat speed minus current is equal to the ground speed. So remember, what they're telling you, this is your ground speed. So think about your equations, the boat plus the current and the boat minus the current, and look at those two. You should write your equations, solve it, and then we will be checking your answer in class. I hope looking at these, we'll be doing lots of practice with these problems so you really get them down good over the next couple of days. I hope this is making a little better sense. Make sure you go back and rewatch anything you need to for better understanding.